Hey everybody, welcome to my presentation, Keep It Simple, but Not Too Simple. Whether we're prospective grad students in math or whether we're math professors, simple examples make up an invaluable part of our repertoire. Yet, of all of the tools in our mathematical toolboxes, examples, and specifically simple examples, seem to be the most neglected. Simple examples give us insight as to how to go about proving conjectures. Simple examples, but not too simple, reveal patterns that can help us form conjectures. And simple examples give us insight as to the application of classic theorems. Now let's consider some examples. In the preceding talk, one of our students, Nam Dong, did a great job of showing that the Tower of Hanoi problem for any number of disks, let's say k plus 1 disks, is such that the process of moving a stack of disks from one peg to another peg is exactly the same, no matter how many disks we start out with. And let's think about this. Let's say that we have k plus 1 disks. So Nam said, here are the top k disks. And what do? We move the top k disks to another peg. That's always the first step, or the first main step. There are several steps that we have to take to make this happen, but this is always the first step. Take the top k disks and move them to another peg. The second main step is always the same. Move the k plus first disk to the destination peg. This is always the second step. Take the k plus first disk and move it to where you want all of the disks to be located eventually. And then the last step, from here to here, move the top k disks to the destination peg. The process is always the same. But you know something interesting? I had played the Tower of Hanoi game a million times before I realized that. Well, okay, slight exaggeration. 1,000 times. We have the game in the math office, and I must have picked that thing up thousands of times and played it. Well, okay, slight exaggeration. Hundreds of times anyway. And it would always end up the same way. I'd play with it for a few minutes, and then I'd say, I'm tired of doing this. I don't want to do this anymore. And then one day something happened. I picked up the game, and some of the disks were missing. Most of them were missing. There were only 3 disks on the entire board. Now, I don't know why. Maybe somebody thought they looked cool and they thought they'd take one home with them and put it on their desk in their dorm room, and it would be a nice topic for conversation. Maybe somebody else took one and put a string through it and hung it from their rear view mirror and thought it looked really neat. I don't know. But anyway, there were only 3 discs left. So I picked it up, decided to amuse myself with it for a couple of minutes, and in about 15 seconds I had moved the tower from one peg to another peg. But more importantly, I saw the big picture, something that I hadn't seen before, and let me show you what it was. Now here's what I saw when I played the game with just 3 discs. Well, of course we have to move the top disc, so I moved it here, what the heck. And of course I have to move the second disc, and so I'm going to move it right here. And of course I have to move the largest disc, the third disc, but there's no free pegs to move it to. And the only disc that I can really move and not take a step backwards with is this disc, the smallest disc. So I put the first disc on top of the second disc. And now I can move the large disc to the destination peg. This is where all of the discs are going to end up eventually. And I'd like to take the second disc and move it on top of the third disc, but I can't because the first disc is on top. So I take the first disc and move it to an open peg. And then I take the second disc and move it on top of the third disc. And then I take the first disc, the smallest disc, and put it on top of the other 2. And there were just enough discs here for me to see what was going on and at the same time not hide what was going on. I saw this and I had an oh my goodness moment, OMG, because here's what I saw. I took the top 2 discs, these 2, and in these 3 steps, I moved the top 2 discs to a temporary peg. So that's step 1. That's the big step 1. Here's the big step 2. Move the bottom disc, the third disc, to the destination peg. So that's the second step. And then these 3 steps constitute the third step. Move the top 2 discs on top of the bottom disc. Or we could say destination peg. So essentially there are 3 main steps. Move the top 2 discs to a temporary peg, that's step 1. Move the bottom disc to the destination peg, step 2. And then move the top 2 discs to the destination peg or on top of the bottom disk. And that is step 3. Well, would it be any different if we had k plus 1 disks instead of 3? Absolutely not. The same process has to occur. Move the top k disks to a temporary peg, and then move the bottom k plus first disk to the destination peg, and then move the top k disks and put them on top of the k plus first disk. The same 3 steps have to happen. No matter whether you have 3, 4, 400, 4,000 disks, the same 3 steps have to happen. Well, before there were so many disks on the Tower of Hanoi, I couldn't see the process. And it's a good thing that when I picked it up this last time, there were exactly 3 disks on the tower, because you know what? If there had only been 1 disk or 2 disks, I wouldn't have seen the pattern. The example would have been too simple. Let me show you. N equal 1 disk, I take the disk and move it to the destination tower. What does that show me? Nothing. N equal 2 disks, well, you know what? If we already know what the pattern is, we can see it here. Move the top disks to a temporary tower. Move the bottom disk to the destination tower, and then move the top disk back to the destination tower. But since there's only 2 disks, we don't really understand that no matter how many disks are on top of the bottom disk, we take all of these disks on top of the bottom disk, move them to temporary storage, and then move the bottom disk to the destination tower. Then move all of the other disks from temporary storage on top of the bottom disk. So n equal 2 disks doesn't really show us this either. We can recognize the pattern here if we already know what the pattern is. But if we don't know what the pattern is, the example with n equal 2 disks isn't going to show us. It's just going to be too simple. So the bottom line, 3 disks is perfect for showing the example. If the tower has less than 3 disks, I don't see the pattern. It's too simple. If the tower has more than 3 disks, I never see the pattern because things get too complicated too quickly, and I get tired of playing the game and I quit before I even finish. N equal 3 disks is the perfect example. It's simple, but not too simple. Now let's consider another case in point, the product rule. And we'll start off with n equal 2 factors. Consider my form of the product rule. 2 factors. First prime times second plus second prime times first. There's a pattern here that can be generalized to n factors. But the case with 2 factors is too simple to bring it out. So let's take a look and see what happens with more factors. Let's look now at the case where we have the derivative of the product of 3 factors. It turns out to be first prime times all the others, second prime times all the other factors, third prime times all the other factors. And if we compute the derivative of the product of 4 factors, we have first prime times the other factors, second prime times the other factors, third prime times the other factors, fourth prime times the other factors. That's the general pattern. But with just the product of 2 factors, we didn't see that. But now that we go back and look at the product of two factors retrospectively, we can see this is exactly what we have. First prime times all the other factors, plus second prime times all the other factors. We didn't see that before because the example with just n equal 2 factors was simple, but it was too simple. Our last example, Burrell Theorem. It says let G be a collection of open intervals. An open cover of the interval AB, that is, the interval AB is contained in the union of these open intervals. The Burrell theorem says G can be reduced to a finite subcover of A. In other words, there are finitely many of these open intervals such that the interval AB is contained in the union of these finitely many intervals. Now, how many of us give our grad students this theorem or our analysis students this theorem and don't give them any examples to show why the hypothesis that this interval be finite can't be relaxed, or the hypothesis that this interval is closed can't be relaxed? Now, here's an example that shows why the restriction that the set of real numbers or the interval A can't be finite. Here's an example that shows that the restriction that A be a finite interval can't be waived. Let's say that A is the entire real number line. And let G be the set of intervals of length 2 with integer endpoints. Well, the union of these open intervals contains the real number line. We can see here that the real number line is contained by the union of these intervals. But I'll tell you what. Suppose that we just remove even one of these open intervals. Let's say this one, the open interval from 0 to 2. Well, guess what? The point 1 on the real number line is no longer contained in the union of these intervals if we remove just one open interval from 0 to 2. So the restriction that the set A has to be a finite interval can't be waived. And what about the restriction that A be a closed interval? Well, it can be shown that the union of these intervals actually does contain the entire set A. But can this be reduced to a finite open cover? If so, we'll just take the largest of these finitely many intervals and realize that all of the smaller intervals are contained in the larger. So the union of finitely many of these intervals is just the largest interval in the collection. And no one interval contains this open interval. No one interval in this collection contains this interval. What's the problem? Well, this interval is not closed. And so even though we have an open cover of this interval, it can't be reduced to a finite subcover. So the bottom line, I'm running out of time quickly here, is we need plenty of examples, especially simple examples. Simple, but not too simple, especially for our students.